So should I try to advance it now? The light looks, but so, oh, okay. Did you adjust anything? Yeah. Huh? If I have to do it manually, I'll just do it manually. You can use this. Yep. Assuming that works. And what I'll do is I'll just use this as because there are people online anyway. Don't worry about it. I'll just use the laser pointer from here regardless, so that the people online can see with the laser pointer on the screen. No, so we're on slideshow mode. So I'll go up. Bang. There we go. All right. Should I take a seat someplace? Yes, please. Okay.
Good afternoon, everyone. I am Shampana Banerjee, an undergraduate first-year student at the Department of Geology. Today, we are honored to host the GSA James B. Thompson Junior Distinguished International Lectureship in Presidency University. Professor Alan Fryar from the Department of Earth and Environmental Sciences, University of Kentucky.
Sound
Junior Distinguished International Lecturer for 2024 to 2025 is here with us. Previously, he has delivered his lecture in Lebanon, Kyrgyzstan, and Turkey. Now I would like to request Professor Shampar Bose, President of the Geological Institute and Head of the Department, to felicitate us. Thank you, sir. Now, let me give you a brief introduction of our speaker. Professor Fryar received his BS in Geology from Duke University in 1984, his MS in Geology from Texas A&M University in 1986, and his PhD in Geology from University of Alberta, Canada in 1992. Following his doctoral studies, he was a research associate in the Bureau of Economic Geology at the University of Texas at Austin from 1992 to 1995. Currently, he is a professor of Earth and Environmental Sciences at the University of Kentucky, where he has been a dedicated faculty member since 1995. His research interests groundwater stream interactions, mass transfer to karst watersheds, chemical evolution during groundwater recharge and flow, natural attenuation of contaminants, and water resources in developing countries. Professor Pryor is a fellow of the Geological Society of America and has also served as chair of GS's Hydrogeology Division 2013. His international contributions are notable, having been a full-time specialist in environmental science to Pakistan 2009 to 10 and in India 2017, a Fulbright Research Scholar in Geology to Kolkata 2014, and a Fulbright Kalam Climate Fellow to India 2023. He was vested with the International Service Award from the IAH US National Chapter and the GSA Geology Division Maxi Distinguished Service Award. So, without any further ado, let us welcome Professor Alan Fryar.
Thank you for the kind introduction. I'd like to thank Professor Rose and all of you for being here today. This is my 8th and final lecture of this leg of the tour. Here in India in May and June, I will be lecturing in Turkey and Kyrgyzstan. So with that, let me go ahead and get started. As was mentioned, I'm here as the James B. Thompson International Lecturer. I'm grateful for GSA for this group. So I'd like to provide an outline first of the talk. There are 3 key concepts here, which may be familiar to you, maybe all of them, maybe some of them, but I want to provide some common definitions. We're going to discuss 3 different case studies in 3 different countries, and I'm going to compare them to talk about how springs respond to erosion and how differences in those responses reflect differences in climate, lithology, topography, geologic structure, and land use. So first of all, defining springs. Springs are really outcrops of the water table, and therefore they're windows into the earth. We typically think of groundwater as something beneath our feet that we can't see. Springs are places where groundwater emerges. They're important because they provide base flow for streams in the absence of rainfall. They're important water sources, especially in rural and mountainous regions, including such regions in India. They're culturally significant for recreation, for healing, and for religious purposes, and they host distinctive, sometimes unique ecosystems. And from a geologic or hydrologic perspective, they're valuable because they integrate information about various processes that affect water along flow paths upstream or upgrading. So just in terms of my personal background, I'm from the state of Florida in the southeastern United States, and Florida is known for having some of the largest springs in the world. These springs feed rivers that flow into particularly the Gulf of Mexico, and I've been going to these springs since I was a child. This is a photograph from about 10 years ago from a family trip along the Greenwood, Florida. So the first term I want to define is karst. That's a landscape that forms by weathering of soluble rocks, mostly limestone, but also other carbonates, including dolomite, which of course is made of the mineral calcium and magnesium carbonate, as opposed to limestone, which is primarily calcium carbonate. Also marble, which of course is metamorphosed limestone. And in some instances, you can have karst develop on a background formed by bed salts such as gypsum and halite in arid regions. The weathering in carbonate rocks occurs primarily because carbonic acid, which moves to the dissolution of carbon dioxide in rainwater or in soil water from the atmosphere or respiration of root zone, reacts with the carbonate minerals and salts. So I'm going to focus on carbonate karst here. Karst terrains are characterized by sinkholes, called in European literature dolines. Sinkhole is really American. Sinking streams, which are streams that, other than during storms, tend to be dry, but may have flow paths that divert into the subsurface from sinkholes in the stream bed. Conduits, which are solution-enhanced flow paths, for example, caves, which are conduits originally from humans in streams. So what happens is that water infiltrates along preferential flow paths, such as fractures and rocks, or moves diffusely through the soil and into these rocks. And then as the water moves along these preferential flow paths, it dissolves away the rock slowly. Therefore, what thereby creates a positive feedback loop. That means that you have increasingly large preferential conduit networks that connect surface sinks to springs. Now, it's worth noting that all karst terrains tend to be marked by springs, but not all springs occur in karst terrains. Carbonates cover about 15% of the ice-free terrestrial surface, and karst aquifers supply as much as 1/4 of the global population, including some large metropolitan areas in the United States like San Antonio and Miami, Vienna, Rome, and Damascus. This next image is a map of world carbonate outcrop areas. The light blue patches are discontinuous or buried carbonate rocks. The dark blue patches are more continuous carbonate rocks. And the study sites in this talk are marked by red stars in the Middle Atlas region of north central Morocco, in the South China Karst, and in Kashmir. And you can note also from looking at the Indian subcontinent that there are places such as the Kashmir Valley, places in Chhattisgarh, and elsewhere in southern India, and in the Meghalaya Plateau where carbonate rocks are pronounced. This is a map of karst terrains in the United States. This shows evaporite karst and what we call pseudokarst, like lava tubes, as well as actual karst and carbonate rocks. That's shown in green, and that's what I'm going to focus on. The darker green is where carbonate rocks are exposed at land surface. The lighter green is where they're buried beneath several tens of meters of overlying sediment or soil. Florida, for reference, is down here. Kentucky, where I live, is here. There's Washington, D.C. Here's New York City, Chicago, Los Angeles. So karst hydrology is distinctive from water flow through the subsurface in other types of geologic material. So if we think about groundwater passing through the subsurface, we typically think of water that is resident in pore spaces between grains, for example. And therefore, that water tends to move relatively slowly under what we call laminar flow conditions. But in karst, because of the potential for development of solution-enhanced flow paths and much larger diameters, you can have turbulent flow. So what this means, first of all, is that karstified limestone and other carbonate rocks are heterogeneous. That means that as opposed to conventional groundwater flow, where you may sink tube wells into an alluvial aquifer and you can map the water table, it's much more difficult in karst. It's really integrated surface and subsurface drainage along almost like stream networks. So these flow paths can be localized and difficult to delineate. And it also means that spring basins or catchments where groundwater discharges to the surface may not coincide with surface watersheds, that you can have interbasin flow. Also, because of the solution-enhanced porosity and permeability, you can have large flow path widths. So instead of simply millimeter or sub-millimeter scale, as you see in conventional porous media, think of caves where you can have diameters of meters. Consequently, velocities can be relatively rapid, as much as hundreds of meters per hour. That is comparable to surface streams. And therefore, karst aquifers are vulnerable to non-point source pollution. That is, pollutants washing in from the surface through these sinkholes, from agricultural terrains, urban areas, and they can also potentially be relatively vulnerable to fluctuations in recharge. That is, during droughts, you may see, or may not, depending, significant reduction in flow. So in terms of the question of how springs respond to recharge, let's define recharge then, which is just the infiltration at land surface that makes it to the water table. And so water that infiltrates or water that hits the land surface can be intercepted before it reaches the water table. It can run off overland or laterally within the soil zone, and water can also evaporate or be taken up by plant roots and transpired. And so we commonly lump together evaporation and transpiration which are both processes that return water to the atmosphere as evapotranspiration. So recharge is the difference between precipitation on the one hand and evapotranspiration and runoff on the other. And recharge is affected by various climatic factors, including the timing of precipitation. For example, what season does the precipitation fall in? Is it cool season or warm season? The amount of precipitation, the intensity, that's what is the rate of precipitation, and the form. Typically, certainly where I live, and I'm sure here, when people think of precipitation, they think of rain, but it could be snow in colder places. And as I alluded to earlier, there are other factors that affect how springs respond to recharge, such as land use, land cover, lithology, structure, and relief. So this diagram left here is just a conceptual diagram from an article in Journal of Hydrology. And I want to focus on a couple of things here. One is the soil that mantles or overlies the weathered top of bedrock here, which we call epikarst. And so you can see an irregular surface between the soil and the top of bedrock, and infiltration is focused beneath the low spot here on the surface. You also see infiltration moving along discrete flow paths here, primarily vertically, downward along joints, and ultimately to the main water table, the top of the phreatic zone, which intercepts this conduit here. So this would be open channel flow, basically within a subsurface stream. But note also, there's discontinuous saturation here within the epikarst where water accumulates, where it's perched on a horizon here that may be lower permeability. And so you see solution enhancements, such as where you see this depression in the top of bedrock here. And that's shown in this photo at right that I took in China. So you can see dipping limestone beds, and you can note vertical fractures, joints that have been widened by dissolution, as well as bedding planes horizontally that have been widened. And one of these joints has been widened so much that you see soil has filled it in and rooting is occurring in that soil. So we can ask, when water infiltrates, what happens to it? So as shown in the previous diagram, it can be diffused through soil or focused beneath depressions such as sinkholes, as well as along preferential flow paths such as fractures or joints. When that water infiltrates, if there is water already residing in pore spaces between grains or in fractures or in conduits, that infiltrating water displaces the water that's already resident. As the water moves through the subsurface, it can react with solids, dissolve minerals, for example. That's how karst features evolve. It can also exchange heat with a solid matrix. And the extent of reaction and of heat exchange really depends on the residence time. That is, how long the water is in the subsurface, as well as the composition of the matrix, what is the solubility of the rock, for example. In terms of how this varies with time, water temperature and water chemistry at springs can vary over different timescales, again, depending upon how quickly the water moves through the subsurface, how well connected the flow paths are. So it could be at storm event timescales, say hours to days after a storm, or it could be seasonal or even longer, so months. In terms of how we look at how springs respond to recharge, there are parameters that are routinely monitored. The first of these is the volumetric flow rate, or discharge. And so some of you may be familiar with the term discharge as kind of a counterpart to recharge, that recharge replenishes groundwater, discharge is where groundwater exits the subsurface. But also discharge refers to the volume rate of flow of water, either groundwater or a stream. And so we can measure discharge by basically going out and waiting, for example, with a current meter across a transected stream or at a spring. And so if you know the cross-sectional area and you know the velocity of the water moving, you multiply them together and you get the discharge. But because discharge is correlated to height through the relationship with cross-sectional area, we can also examine that correlation by developing what's called a rating curve. And so basically you measure discharge over a range of water heights or stages and develop an empirical relationship that's site specific. We can also monitor water temperature using a thermometer or thermistor. We can monitor electrical conductivity or specific conductance, which is just electrical conductivity at a reference temperature like 20 or 25 Celsius. And electrical conductivity and specific conductance are correlated to total dissolved solids, or salinity, really. And the thing about monitoring stage or water height, water temperature, and electrical conductivity is that all of those can be continuously logged. We can put out a water level indicator, basically something that measures water pressure, or we can put out a thermistor, or we can put out a conductivity electrode connected to loggers and get continuous measurements. And that can be really useful in terms of looking at time series responses. We can also go out manually and collect water samples to analyze concentrations of solvents, major and minor ions, metals, nutrients, etc., and isotopes. And so I want to point particular to stable isotopes of water. So you may remember that an isotope is a form of a particular element with a particular mass. Different isotopes for a single element have different numbers of neutrons. And when you think of isotopes, you may think of radioactive isotopes, such as isotopes of uranium, plutonium, but we also have stable isotopes. So for example, if you look at hydrogen, the main form of hydrogen is hydrogen 1, with 1 proton, no neutrons. There's also deuterium, or hydrogen 2, which has a neutron in addition to the proton. If you think of oxygen, you probably think of oxygen and the atomic mass of oxygen is 16. Well, oxygen 16 is the main stable isotope, but there's also oxygen 18, which has 2 extra neutrons. And so if we look at the abundances of these less common stable isotopes, then we can infer information about where water is coming from when it provides recharge and about the processes that affect water after recharge. And so this next slide shows this a little bit better. This is a process called isotope fractionation or enrichment. And you'll sometimes hear this referred to in isotope geochemistry as Rayleigh distillation. And so what happens is if you look at a water body here, you have mostly oxygen 16 and a minor amount of oxygen 18. But when that water evaporates, the oxygen 16 preferentially goes into the water vapor because it's lighter than the oxygen 18. So the residual water that's not evaporated tends to become more enriched in the heavier isotope, oxygen 18. If that water that evaporates then condenses, that water that rains out or that snows out has more oxygen 18 compared to the residual water vapor. So you get this progressive distillation process. You see the same thing with hydrogen 2 compared to hydrogen 1. Because these less common stable isotopes have relatively low absolute concentrations, what we do when we analyze them is we compare them to a known standard, like seawater, for example, and then report the concentrations in relative units of parts per 1,000 or per mil using this delta notation here, the lowercase Greek letter d. And so we talk about delta 18O, which is relative concentration of oxygen 18, or delta 2H, which is relative concentration of deuterium. And it was realized in the early 1960s by Harman Craig that if you took precipitation samples, rainwater or snow, from around the globe and plot delta deuterium versus delta oxygen 18, that you get a line that has a slope of about 8 and an intercept of about 10. And we call this the global meteoric water line. And so precipitation samples tend to follow along this line. If you look at local conditions and have what we call local meteoric water line, the slope may differ a little, maybe 7, the intercept may differ a little, but it's pretty similar globally. And so what this means is that under warmer conditions or lower latitude or lower altitude or coastal conditions, that is close to the source of the moisture, like the Bay of Bengal or the Arabian Sea and peninsular India, that you tend to have higher relative values of delta deuterium and delta oxygen 18. So this would be, for example, associated with conditions in the summer, where you have cooler conditions or higher latitude or higher altitude or farther inland. So think of an air mass with monsoon and it's progressing from the Bay of Bengal or the Arabian Sea across peninsular India and it progressively rains out. Then you get, as it moves farther inland, higher elevation, farther north, you get more negative values of delta deuterium and delta oxygen 18 because it's depleted in the heavier isotopes. Finally, I want to note that when water evaporates, if it doesn't evaporate completely, that the oxygen 18 is left behind more than the deuterium is left behind because this is higher mass. And so what that means is you get a trend with a slope that's lower than the meteoric water line. So that slope may be less than 6, for example. So I'll show examples of these later. In terms of how a spring responds to precipitation, I tell my students this is like turning on a faucet or turning on a garden hose. That when you do this, if the pipe or the hose is filled with water, you automatically get water coming out, but that water is not new water. That water is the resident or older water that is being displaced by the water that's coming in behind it. And so this represents a pressure pulse in the case of karst moving through a flood conduit. And so what happens is, as you in effect turn on the faucet by introducing recharge, the discharge Q goes up, and then there's a time lag after which the electrical conductivity starts to decrease, the salinity starts to decrease, because you get this newer, presumably more dilute rainwater, snow melt arriving at the spring. And then conversely, once you've hit peak discharge and it starts to recede, then you see a reversal, and that newer water has passed through the system. You get older water coming out of the matrix falling in behind it, and your electrical conductivity starts to recover back toward its higher baseline value. Temperature of the water at a spring can decrease or increase, and that really depends on the contrast between the water temperature and the air temperature. So in general, below a depth of 10 to 25 meters below land surface, and within perhaps 100 meters depth of land surface, air temperature tends to be relatively constant and tends to be within about 1 degree Celsius of water temperature tends to be relatively constant, tends to be within about 1 degree Celsius of annual average air temperature. And so what happens is, if you have recharge during a cooler time of year, that recharge may be colder than the water that's already present in the subsurface. And so you'll see a temporary dip in water temperature. Or conversely, in the summertime, that recharge may be warmer than the water that's already there. And so you'll see a temporary increase in water temperature coming out of the spring. Again, this really depends upon how long it takes the water to move through the subsurface, because it can basically exchange heat as it's doing this. So as a result, overall, what we see is at longer timescales, seasonal to annual timescales, you can see no response to recharge. That is, that you have relatively inefficient flow paths in terms of water moving quickly, and therefore you get heat exchange kind of dampening out the temperature difference. Or you can see an oscillatory temperature pattern, which is basically a reflection of conduction of the seasonal air temperature signal moving through the subsurface. And so it's lagged and it's dampened in terms of looking at the water temperature of the spring. Or you may see erratic patterns. That means that the water moves relatively quickly through the system, and so you see responses to individual storm events. And all of this, which kind of pattern you see really depends upon how efficient the heat exchange is. So this is just representative diagram from work I did about 20 years ago with my students in Central Kentucky. By the way, the name of this town is pronounced Versailles. That's how they say it in Kentucky, not Versailles, like in France. So the dates down here are typical American notation, month, day, year. So January of 2006, this is over a period of about 2 days. And what you can see is that as a result of precipitation, of rainfall, which is shown on the left-hand y-axis by the blue line, that you see over a period of about 18 hours, there are several pulses of rainfall, multiple millimeters. And therefore, the discharge, which is shown on the right-hand y-axis in cubic meters per second, and the gray line increases as a result of rainfall. As the discharge starts to increase, there's a time lag of an hour or more, and you can see the specific conductance shown on the right-hand y-axis starts to decrease and the water temperature shown on the left-hand y-axis also starts to decrease because this is winter, so you have cooler water coming in. And then as the discharge starts to peak, the specific conductance reaches its minimum and the water temperature starts to bottom out, and the water temperature starts to recover, and the electrical conductivity or the dry solids start to recover as you get recession and discharge. So looking at temperature responses then, at top you can see here, this is from the state of Minnesota in the northern United States or in Canada. The air temperature trend is shown here, and it's sinusoidal, maximum in summer, August basically, or late July, minimum in winter in January. And you can see that the overall temperature ranges from plus 30 to minus 30. But you see the sinusoidal trend representing the smooth pattern. Precipitation is shown here at right, and you can see, as I was talking about with some of the professors earlier, in this part of North America, you don't really have wet and dry seasons. You just have some months that are wetter than others. But you can see clusters of precipitation. The bottom diagram here shows temperature on the left-hand y-axis, and this represents the red line, and water level on the right-hand y-axis. And again, you can see as you have water level fluctuations, you have synchronous temperature fluctuations, and then it kind of levels out for a while during the winter time when there's not much infiltration and the ground is frozen. Then you start to see a recovery again during the next warm season. This is taken from a paper in Groundwater. So again, what I want to do is compare these three case studies to highlight a range of responses, to look at what we can infer about hydrologic behavior from how springs respond in different settings and how the various factors that I talked about interact to control how well the flow paths are connected, surface and subsurface, and therefore how springs respond to external forcings. And so this has implications for understanding how climate change can affect spring flow, how land use and land cover change, like urbanization, can affect spring flow, and also how water quality in springs is susceptible to human activities, how quickly it may be impacted. So my first case study is from Morocco, where you have karst developed in carbonate rocks, limestones, but also dolomites. This is a high plateau, relatively high, sort of similar to the Meghalaya Plateau in Northeast India. And because of the extent of magnesium in the rocks, you don't get as much karst development. There is faulting here, alpine tectonism in Western Mediterranean, and so that promotes preferential flow, but the extent to which you get karst features developing is limited by the solubility of the rocks, the fact that you have dolomites and magnesium limestones. It's a Mediterranean climate with dry summers, so it's kind of the inverse of South and Southeast Asia. There are wet winters or late autumn, winter, early spring seasons, and dry times, other times of the year. Rainfall from about 600 millimeters per year at the foot of the plateau to about 1,000 millimeters on the plateau. And Morocco has been in drought for much of the last several decades, and it's projected to be a climate change hotspot. And land use, land cover is mixed up on the plateau, but the soils are relatively thin and have been affected by overgrazing and deforestation. So at left is just a map of the study area. Here's Morocco, here's Spain. At right is a Google Earth image, and I want to focus on the three places circled in red, which represent springs: Riba at the base of the plateau, Saruca and Sidi Rashid, two springs on the plateau. These are all municipal water supplies. I also want you to note this north-south line of cross-section, AA prime. So this next map is basically the same area. It's from a paper in Hydrological Sciences Journal. The previous images were from a paper I published with colleagues in Hydrogeology Journal. So you can see the plateaus here indicated by Liassic or Middle Jurassic rocks in this dark gray stippled pattern, and you can see features that are associated with preferential flow, such as large fracture sets, kilometers long, and karstic depressions and sinkholes. Here's Riba Spring for reference, another spring I won't be talking about. And then an intermittent river that comes off the plateau that only flows basically during the rainy season. So this is that line of cross section I pointed out in the previous diagram. And I want to point out elevation here. This is almost 1,500 meters above sea level. The plain down here is about 500 to 700 meters above sea level. So you've got pretty significant relief. And this blocky pattern up here represents where those Jurassic carbonates, the limestones and dolomites are exposed. This is what the plateau looks like during the cool season when recharge occurs in February. Again, you can see the kind of thin rocky soils and the patchy forest cover. And this is what it looks like later. Again, you can see the relief here. Similarly, this is February, and the spring at the foot of the plateau is flowing pretty vigorously. Much of the water in the spring house is diverted by pipes to the city of Meknes, and this is the water that overflows over the head gate. But later in the year, in September, at the end of the summer, you can see the flows have declined and you don't see any extra water flowing out from the spring house. This is a plot of stage or water level height relative to arbitrary local data for the two springs on the plateau. And what you see here is at right is precipitation, and you see clusters of precipitation spikes. But for the most part, you don't see too much precipitation between April and October. And so as a result, you can see that the water level, although it fluctuates daily, generally declines before rebounding in autumn and then leveling out and starting to decline again. And I think the reason why there's a greater amplitude for one of these springs than the other is there's greater water diversion for municipal use during the summertime, because this is basically like a hill station. It's a tourist area. In terms of the temperature signals, the color scheme is the same as the previous slide. So you've got blue representing one of the springs on the plateau, yellow representing another, and gray representing the spring at the foot of the plateau. So for the first spring here, you can see that the response is relatively flatline. I joked that if this were, a heartbeat, the patient would be dead. The second response here is sinusoidal with some spikes shown here, but generally oscillatory. And the third at the foot of the plateau is interesting, that you see it's relatively flat. And then once you get into November, that it picks up and starts to fluctuate. And so it's as if, the patient's heart had stopped and you're doing CPR to resuscitate the patient. Note that for the two springs up on the plateau, which again are several hundred meters higher, the temperature scale is about 11.7 to 12.7 Celsius. At the foot of the plateau, it's about 4 degrees warm, 15.8 to 16.8. So what we infer is that there's a deep, relatively slow flow path on the plateau for the one spring that basically has had the temperature fluctuations completely dampened out. For the other spring on the plateau, we think the flow path is shallower, thus you're seeing a conductive signal. And in the spring at the foot of the plateau, we see basically a response to when the rains start. So looking again at this yellow trend here for the spring, one spring that we think has a shallow flow path, you can see again the spring signal here in water temperature left. And then this is plotted against air temperature at the local weather station, shown relative to the right-hand signal. And you can see that the two graphs are out of phase with each other, that the minimum and maximum groundwater temperatures lag the minimum and maximum air temperatures by several points. So this is a plot of delta deuterium versus delta oxygen 18. This is what we call the local meteoric water line for the city of Fez. Slope is about 7. And you see that these values scatter around the meteoric water line. There's a little bit of values below the line, which suggests there may have been some evaporation. This represents a data set of samples collected every day for just over a year from one of the springs on the plateau. And what I want you to note inside this ellipse is there are some samples that have more negative values. And so if you, in turn, instead of plotting delta deuterium versus delta oxygen 18, plot delta oxygen 18 and delta deuterium as a time series, and these represent 10-point moving averages or 10-day averages for smoothing. You can see that they're in sync in the cool season and out of sync in the warm season. And so we think the fact that they're in sync in the cool season and less evaporated shows that the cool season rainfall is just refilling the lava. So basically the result here for the Middle Atlas springs then is that the water temperature signals for the springs on the plateau indicate thermal exchange is pretty efficient. Flow is not conduit dominated. You don't have a lot of karst development. You've got flow moving through fractures for the most part. Whereas the spring at the base of the plateau appears to be fed by two flow systems. That during the dry season, when you don't see much of a temperature variation, you've got a long, slow flow system that dominates coming from the plateau. But during the wet season, we think what's happening, if you remember that map, and I mentioned the stream that comes from the plateau, we think water is sinking down from that stream bed, and that's causing those temperature spikes. And then the fact that we see the delta deuterium and delta oxygen 18 signals moving in and out of sync suggests you've got changes in sources of recharge, moving from less evaporated during the wet season to more evaporated during the dry season. And this suggests overall that this system will respond to drought relatively slowly, but it will also refill relatively slowly. So the second case study is in South China in the Hozhai Basin, spring shed or spring catchment of about 74 square kilometers. The classic cockpit karst developed in faulted Triassic carbonates. They're overlying clay soils. This basin has been studied by people at the Chinese Academy of Sciences for over 2 decades. So we were kind of building on a lot of work that had been done, was being done simultaneously. And part of that work had kind of mapped the existing conduit network in the subsurface. You can imagine it's relatively easy to map surface streams. It's a little bit harder to map where streams are flowing in the subsurface. You have to map waves, among other things. So we built on that work. Like South Asia, this is a monsoon climate. It's kind of on the transition geographically from the Indian summer monsoon to the East Asian summer monsoon. Precipitation is about 1,300 millimeters a year. And what happens is with cave systems or with conduit systems, as they develop, they often respond to base level changes, a downcutting of the main streams in the area. And so what that means is you get multiple levels of passages. And so what happens is during monsoon, the water table can rise back up into higher level or overflow passages. Like in Morocco, land use and land cover are mixed. Besides agriculture and forests and towns, there's also industry, production of cement and limestone mining. And like in Morocco, there's been some degradation and what we call karst rocky desertification, where there's been loss of soil. So this is just the South China karst region, 8 provinces in southern China with our study area right in the middle in Guizhou. And for reference, you can see here's Beijing and here's Shanghai. There's Guizhou province. So this is a digital relief map of the karst basin. And you can see the highest elevation of about 1,550 meters is in the eastern and southeastern part of the basin. The lowest elevation of the outlet spring at 1,210 meters is out here. So you've got about over 400 meters of relief in the basin. And what I want to note, first of all, here are these solid blue lines, which represent surface streams, and these dashed blue lines, which represent the subsurface conduit networks. Note they're interconnected, but it's not just like a surface stream network where you have tributaries coming in to create larger streams, that you can see these pathways bifurcating, coming back together again. It's almost like a braided stream network by analogy, or in Ganges Delta, where you have splitting of passages or stream channels and coming together again. Each of these dots with a letter represents a monitoring location in our study, either a sinkhole or what we call a karst window, where you've got the collapse of the overlying rock and you're basically exposing the cave locally, or springs. So this is the title slide again of the classic peak cluster topography of South China, these sort of rounded hills or karst towers, again, paddy in the foreground. You see the surface channel, and the subsurface channel passes beneath. This is one of these karst windows after several days of rainfall in June of 2017. And 5 days later, after several days without rainfall, you can see how responsive this is. It's like a bathtub draining, about a 10-meter fall in water level. And this is the outlet spring at Maochuakang, and you can see there's a lot of instrumentation here already. So part of what we did that hadn't been done as much in the basin is dye injection. So what you can do is inject a fluorescent dye, non-toxic, artificial, so it doesn't tend to occur naturally, so you don't have much of a baseline, detect relatively low concentrations. And so we did that in this karst window. We observed it coming out at the spring. Ideally, you don't have to put so much in that you actually change the color of the water. It doesn't have to be visible. You can detect it on what we call charcoal bugs or packets onto which the dye absorbs, and you extract the dye and analyze it with a spectrophotometer. But in this case, we put a bit much dye in. So I joked that the goose here is kind of pointing at us and how dumb we were with the amount of dye we added. So we did 3 sets of dye traces through the basin. The first was shown in that previous slide where we injected here and we detected at the spring that I showed and at several other springs. And you can see we detected along 2 different flow paths here that split and then came back together before coming at the outlet spring. This was during base flow after several days without rain in the summer of 2017. Sorry, 2018 rather. We repeated this later that same month after storms. And what you can see here, I've drawn arrows or flow vectors that are thicker, qualitatively indicating greater discharge rates, greater velocities. Note also, in the previous slide, I had inferred flow coming in as a tributary here, interbasin flow under this divide. But we noticed actually gradient reversal here, and I'll talk about that in a minute. And then finally, my student Josh Farner repeated this in the wintertime. And at that time, the water table had fallen because it's dry season. You don't see flow on this passage. You see it along the main conduit passage here. But again, we see a gradient reversal during the dry season. In terms of the outlet spring, I want to show a couple of related diagrams. At right is precipitation, shown here with these spikes. At left is electrical conductivity. Also at right is water level. And so if you look at the darker gray colors here, in response to precipitation, the electrical conductivity immediately doesn't show a decrease. It's actually peaking. Meantime, the lighter gray, the discharge starts to rise. And then as the discharge starts to rise, the electrical conductivity starts to drop. And then conversely, as the discharge starts to peak and drop, the electrical conductivity starts to recover. So I'm just going to focus on the electrical conductivity and water level trends now in color. And so you can see here what I was saying before. EC is on the left, water level is on the right. And so you can see water level starts to rise and then EC starts to fall before reversing their patterns. And so again, this lower electrical conductivity means you got the dilute storm flow coming out of the spring. So this is a plot, and the reason I had along each of the lines previously kind of different colors, like transitioning to different shades of gray or from blue to yellow or red, is I wanted to focus, go back here, so blue to gray, red to yellow. This stretch of each of these plots is represented by when we started taking hourly measurements of temperature and hourly samples for isotopes and other solutes at the outlet spring. And so oxygen 18, delta deuterium is not shown here, but it behaved the same. It's on the left, temperature's on the right, plotted versus date. What you can see here, water temperature shown in the dark dots dropped, rebounded, dropped, and then rebounded again. Whereas water isotopes were more complicated. They rose, fell, rose, fell, rose, fell, rose. So we think these troughs in the water temperature and the water isotopes represent pulses of water coming through from different parts of the basin, upstream, upgrading to the spring. But the question is, why would you see more fluctuations for isotopes than you do for temperature? So more in a moment. Looking at isotopes, again, plotting delta deuterium versus delta oxygen 18, there are several things plotted here. These long kind of cross patterns here represent ranges of deuterium and oxygen 18 for rainfall near the headwaters of the basin and for other sites that have been studied for a long time by other researchers. And so we plotted the means here, and then we plotted the samples that we ourselves took relative to the global meteoric water line. And what you can infer is that as you move up in elevation, or as you move from summer to winter, your values of delta deuterium or delta O18 become more negative, as you would expect. So just to summarize the results from the Hojai Basin then, these dye traces show tributary flow reversals. In the summer, we think it's because of storms, gradient reversals. But in the winter, we found out there's pumping on that tributary conduit for construction. We found that the water isotopes tend to be more positive, more enriched in the heavier isotopes in summer and at lower elevation, as we expect. There doesn't seem to be much evidence of evaporation, so we think infiltration is pretty rapid. Again, for temperature, we saw 2 temperature drops and a rebound in between, which suggests you're getting 2 storm pulses. But the isotopes showed 3, which we think suggests that you're getting recharge from progressively farther up the basin or from different parts of the network. So finally, India and Kashmir. So this is the Littor Basin, the upper Jhelum, tributary of the upper Jhelum Basin, which is a tributary of the Indus, and the Kashmir Valley, much larger basin, about a factor of almost 20 bigger than the previous basin. And the Kashmir Valley's more than half is covered by karst, mainly Triassic limestone. It's a major water supply. Average annual precipitation is about the same as in the Chinese study, but the weather systems are different. As you may know, in this part of India, most of the precipitation comes from what they call the western disturbances from the Mediterranean and the Black Sea, and only about 20% precipitation is monsoon. Again, like the 2 previous studies, you've got a variety of land use and land cover, but this includes snow and ice. So just for context, we know from previous studies that ice mass globally is decreasing with global warming, and you can see the retreat in the extent of mountain glaciers across the Western Himalaya. So from a couple of different papers. And this is yet another paper published in Science that looks at climate change projections and what river hydrographs might look like in the middle of this century. And you can see that of major rivers coming off the Tibetan Plateau, the one that's likely to be most reduced in terms of its peak flow is the Indus. And that's because the Indus is susceptible to glacier melt and snow melt, less snow. So this is our study area, the Littor Valley. We're looking at Martennog Spring, which is near the outlet of the valley. And you can see at the upper reaches here, which are above 5,000 meters. Come on, I'm going to squint. So yeah, 5,300, and the minimum is about 1,600. So you've got lots of relief. So this spring at Wright, my colleague, Professor Ghulam Jilani at the University of Kashmir, and his students have been monitoring for a while. And so this is a photo I took 5 years ago of Pahalgam, halfway up the valley, where there's an IMD station. This is just residual snow on the ground. So the glaciers are kind of in the background behind this field of view. So Professor Gilani and his group monitored stream stage, or spring stage rather, continuously with a gap in the middle for various logistical reasons. And you can see for air temperature from IMD, you get the fluctuations you'd expect. And so basically, as you're seeing peak air temperature, you're seeing a decrease in water level and therefore discharge in the springs. But it's a pretty regular response. So summer, winter, and my student, Shashir Sarkar, who did this work, looked at satellite data and mapped out snow cover from satellite images. And again, you can see snow cover is maximum. So this is shown at left from a paper that I co-authored with Professor Gilani and others, where you get maximum snow cover in January, minimum in October, and unmixing calculations from isotopes and electrical conductivity and solutes tell us that most of the flow coming out of the spring is actually from snow melt, and secondarily from glacier melt, and rainfall is less of a contributor. So what Shashir did was he looked at how, through statistical time series analysis, the stage of the spring responded to different meteorological parameters. So what he found was that the spring was much more responsive to maximum or minimum air temperature than it was to rainfall, and that there was a lag of about 2 to 4 weeks behind temperature fluctuations. He also did machine learning projections based on IPCC scenarios to look at stage changes in 2030. So you see here the historical stage range, minimum in January, maximum in August at Martennog. And then you see the projections here, and they cluster pretty closely together for different emission scenarios. But what they say is that the stage is projected to increase in the winter and decrease in the autumn. So just to summarize, the spring response indicates moderate karst development, relatively high storage capacity. The time lag is also associated with the fact that this is a bigger basin. And that delay between recharge and discharge, as indicated by the spring stage, is more strongly correlated to snow and ice melt than to rainfall. The spring flow increased historically from late winter into early spring, decreased during the dry season, summer and autumn, but with increased greenhouse gas emissions, we expect to see flow reduced further during the dry season. So just to review, to compare and contrast the spring responses, in Morocco, we had limited karstification, so we didn't see pronounced responses to individual storms. And this means that in response to drought, you'll see relatively slow drainage, relatively slow declines in discharge, but there will be declines. In South China, better developed karst means you've got relatively rapid responses to individual storms. And as you have amplification of the water cycle associated with global warming, that storm intensity will also be visible, I assume, in discharge. So this means, for example, you've got the conduit network filling during monsoon rains. And then in Kashmir, you see lagged responses to precipitation consistent with seasonal snow and glacier melt, but we think that projected temperature increases and the melting of snow and ice will increase winter flow and increase autumn flow. So just to summarize then, in conclusion, the spring responses to recharge in all of these cases reflect differences in precipitation, when it falls, how much falls, how intensely it falls, is it rain, is it snow, aquifer lithology, you're talking about limestone, dolomite, and that's the extent of karst component. Land use and land cover, is it vegetated, is it bare rock, is it urbanized, and how big is your basin and what's the relief? And so finally, the susceptibility of springs to environmental changes like land use, land cover, and climate change is going to vary with these factors in complex ways. And so this has got implications for how we use springs, for ecosystem services they provide. And this is all in the context of climate change, amplifying extremes of precipitation and droughts. You get wetter wets and drier dries. So I'd like to thank my students who were involved in this project, my colleagues in Morocco and China and the US, our collaborators, and our funders. And if we have time, I'd be happy to take questions. Thank you.
Thank you, sir. Please raise your hands if you have any questions.
And as an incentive, I mentioned to the graduate students previously, I've got swag here from GSA. So, pens, lapel pins that say I belong, a few cool Triceratops dinosaur bottle opener keychains, and geologic timescale stickers perfect for putting on your laptops or whatever else you like to put a sticker on. So basically, you have to ask me a question to get one of these. This is for the students. Faculty, I'm sorry, you're excellent. Yes. If there's anything left over, if you don't ask the question, you just pick up the leftovers, and then the faculty gets to pick up the leftovers. So yeah, if we have time, I know Professor Mukherjee, my host, my IT director, was supposed to be here soon with my wife, but I am happy to take questions in the meantime of any sort. I tell people they're never dumb questions, they're just dumb answers. So by all means. Now, if nobody asks questions, I'm just going to give the bag to your HOD, and he gets to decide. He gets the swag. I know somebody here is burning to ask a question. All right, I see a hand. Excellent. It's going to break the ice.
Thanks for the talk.
Sure.
My question is, as you stated, changing flow dynamics of these springs, how does it change the associated aquifers in the law, considering climate change and precipitation changes?
So, can you repeat that one more time? How does it change what about the aquifer?
The aquifer properties.
Aquifer properties. Excellent. So the thing about karst is karst flow systems, I mean, you can have relatively rapid sinkhole collapse or with different flow paths being activated, sedimentation or flushing of sediment as a response to storms. But if you're talking about matrix properties, typically you're talking about evolution over timescales that are longer than human timescales, maybe millennia, but still slower than standard groundwater flow timescales. And so basically, as you can imagine, what you get is a system where you have greater permeability, greater secondary porosity, causing the greater permeability. But it's much more heterogeneous and much more isotropic. It becomes progressively, spatially more variable as a result of this sort of positive feedback. So excellent question. Yeah, that's what's really distinctive about karst. Okay, so our person holding the microphone also gets to be kind of game show host. We hand out the bag and you get to pick one item out of the bag. Okay. I could just use my professor voice here and just yell. That's fine. I have to have my. Yeah, go ahead.
Thank you for the talk, sir.
Wait for the mic.
Well,
Okay, go for it.
so it was wonderful talk.
Thank
you. My question is a bit based on some observations I just made last week. Okay. So I was in the field and I'm working in a small spring shed in the state of Kolkata.
Okay.
And in the area where I was working, the extent of classification was almost invisible.
Right.
Yet one interesting observation which I saw was that the springs were almost seems to be retreating or drying up because of the recent change, but the quality was improving in the summer season with respect to monsoon season. So what would be the possible reason? Because it was quite intriguing for me as well.
So what I would speculate then, and this is just complete speculation, is you're having reduced base flow that explains your reduced discharge in non-monsoon season. But what that suggests is that during monsoon, most of the flow that you were getting is meteoric recharge, is basically rainfall, which has relatively little time to react with the rock. Whereas previously, that rainfall was diluting the base flow that was probably more mineralized. So that would be my guess.
So we think that it is somehow linked to the climatic changes.
That would be my speculation. I know that in Kashmir, for example, they were talking about some of the springs that are shallower, not Martin, but one of the other springs. They use the term drying up. It's not quite right. It stopped flowing. So there was still water there, but there wasn't really water coming out. There was very reduced flow. So we might call it seepage. And then what happened, they had a relatively dry winter this winter, but then they had some late rains and snowfall, and then the snow started picking up again. And so in contrast to the spring that I showed, 10, this was like the next basin over. And that was one where there was probably shallower circulation, a shorter flow path, and therefore it responded more quickly to rainfall. But I suspect, yeah, that overall spring drying across the Himalayas appears to be driven by climate change. But in addition, deforestation and other factors don't help cover, can basically retain some of the water. And even though some of that gets intercepted and transpired, it also promotes infiltration. So good question. Thank you. So are you faculty? Are you eligible for? Yeah. Okay. Okay. Sorry. No sticker for you, unless there's one left over. Okay. Other questions? So is this where I kind of poke you on questions at crop? You can represent presidency here. Come on.
Thanks for the nice talk. I have a question. How data eating value was considered as a must-have content in the spring
I'm sorry, can you say that again? What about the moisture content in the spring?
Yeah, like in the delta 18 value, you considered in the spring water how moisture content was considered in delta 18 values.
Okay, so moisture content doesn't necessarily correlate to delta 18O values. All of these were groundwater samples, so they were all fully saturated in terms of the samples being taken from below the water table. What I will say is that moisture content can affect 18O, delta 18O or delta deuterium if the water you're looking at has been partly evaporated. So you can imagine if you have unsaturated conditions, if you're looking at soil water, where not all the pores are filled with water, the water that you extract, if it's been partly evaporated, will have values that tend to trend along that lower slope that I talked about. But for the samples that I collected, I don't think they really reflected a difference in moisture content. Rather, these from Morocco at least reflected a difference in seasonality, that the value of delta 18O or the value of deuterium changed with, is it winter water that's been recently recharged, or is it water that was recharged in the summer that's been there? Sure. No. One per. Somebody else has to be the enforcer on that. Okay, there they are. My hosts are here. Okay, go ahead. Sorry, I'm still giving away goodies.
Thank you for the talk, sir.
Sure.
I have a question about methodology, basically.
Yeah.
Talking about different geochemical processes or geochemical things. But to know the substance of this thing, we always use, or we often use geophysical terms or different surveys. Is there any survey you are doing here?
So I haven't done geophysical surveys as any of the work that I talked about here, but in China, there were other people who did electrical resistivity to try to map out some of these karst conduits. And I haven't talked about any of my work in Kentucky. I've been doing work in Kentucky for over 20 years, but also electrical resistivity and self-potential have been used to map karst conduits as well. So they can be pretty useful for mapping anomalies, and you can then go in and drill or do other investigations to confirm that that's where the water is flowing. Sure. Okay. He gets one. All right. My right is here, so I'd like to introduce and thank my other hosts, also Professor Mukherjee from IIT Kharagpur, his wife Abira, his mother Mrs. Mukherjee, and my wife Dr. Carol. And so they've been very patient with me the last 3 weeks, and we're going to go to Balurmov and go watch people worship at Balurmov. So, are there one other final question before I go? Otherwise, somebody has to decide about how stuff gets parceled out. Going once, twice. Thank you very much.
So this brings us to the end of today's session. Thank you so much, Professor Fryar, for this wonderful presentation. We are also deeply thankful to our esteemed alumni for their unwavering support and continued engagement with the Institute. Finally, I would like to express our sincere thanks to the authorities of Presidency University, Kolkata, and the department staff and teachers for their constant support and guidance. Thank you, everyone.